Welcome to the second part of the course. My name is Chris. I'm a PhD researcher in the Quantum Computing Division at QTech. And my focus is on applying quantum information theory to model and optimize noisy quantum processors. I would like to guide you through the main differences that quantum platforms can provide on a fundamental level, which I believe to be the properties that provide a quantum advantage. Those being the superposition principle, the reversibility of quantum gates, and entanglement, which is a new type of correlation. Before we jump into technical aspects, I would like to quote the theoretical physicist Richard Feynman. Feynman is known for many advances in the modern era of theoretical physics, but especially for the path integral formulation of quantum mechanics, the theory of quantum electrodynamics, and he is also credited with pioneering the field of quantum computing. In 1981, he conducted a keynote speech on simulating physics with computers, where he emphasized the following. Nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. With this in mind, let us start. The first feature of quantum computers is the fundamental unit of computation, the quantum bits. Here we will compare classical bits and quantum bits. As a reminder, classical bits can be thought of as turning off or on some switch, represented as zeros and ones. Thereby, we can encode information by a string of these zeros and ones. One piece of information is encoded in one bit. On the other hand, we have the quantum bits, or qubits for short. The striking feature of qubits is that they can be in a linear combination of zeros and ones, as described by this first state, psi1. One can represent this state on a sphere, where the north and the south poles describe the classical bits. However, qubits can trace out any point on the sphere. On top of that, we can describe multiple qubits together, and here we'll see the real advantage. For 2 qubits, we can describe an arbitrary state psi2, which can be represented in a superposition of 4 possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. If we continue this pattern for an arbitrary number of qubits n, we find that the quantum state can be in a superposition of 2 to the n states. This means that we can encode and represent 2 to the n bits with only n qubits. The second advantage comes from the description of quantum mechanics, namely the fact that quantum gates, which transform one quantum state to another, are reversible, meaning that if we apply the inverse gate, we will get back the original quantum state. This is not the case for classical gates, so let us focus on an example to illustrate this fact. In the classical case, we find the XOR gate. This gate will differentiate whether the 2 input bits, A and B, are the same, returning 0, or different, returning 1. Another way to think about this gate is that it will flip the value of the bit B if A is 1, and then will return the updated bit B. One drawback of the XOR gate is that if we just look at the resulting bit, we will not be able to recover the initial bits A and B. This is different for the analogous quantum gate, the CNOT gate. Here again, it will flip the bit of the second qubit depending on whether the first qubit is in the 0 or in the 1 state. The difference, however, is that the output is a full quantum state, which allows us to recover the initial state as the output states are distinguishable. The technical term for this is that quantum gates are unitary operations. The last, but also most abstract feature of quantum bits is the phenomenon of entanglement. Entanglement is a purely quantum mechanical correlation, which does not occur for classical bits. In the simplest case, entanglement can be described via 2 qubits. We can illustrate several forms of correlation via the density matrix of a quantum state, as shown in this table. Here you see 3 different forms of qubit correlations: independent, classically correlated, or entangled. As you can see, the density matrices look very different between these 3 forms of correlation, which can be seen by the rank of the matrix. Entanglement can be used for very unintuitive protocols. For instance, quantum teleportation, which allows us to teleport a quantum state, and superdense coding, which allows us to send 2 classical bits via 1 quantum bit. This brings us to the conclusion of Module 2.1. To recap, we have been talking about the mathematical advantages of qubits above classical bits. These include the superposition principle, the reversibility or unitarity of quantum gates, and quantum entanglement. In the next module, we will talk about possible applications of quantum computers that rely on these features. See you next time.